Yamashiro さん、よろしくお願いします。
ありがとうございます。ではですね。
Yamashiro-san. Okay, thank you very much. I'm CEO at JIJ. My name is Yamashiro, and we are developing algorithm, and we also have some products, both of which are something that I'd like to share with you today. So I'll start off with for those of you who may not know about JIJ, I'd like to introduce what we do at JIJ. So we at JIJ Incorporated we were basically the researchers focused on the quantum annealing. So annealing or the optimization computation are the ones that we were focusing on in developing software. We are a Japanese startup company. We at JIJ, since yesterday, I get a lot of questions. How would you pronounce this name, my company name? Is that Japan something? Like overseas guest asked me. But no, we are researchers at annealing and easing model. This is the formula in which it's a magnetic model. There's a JIJ. This is alpha. We picked up alphabet from this formula. So if you look at it, there are a lot of physicists. As a matter of fact, JIJ. As soon as they look at this logo, they know we have something to do with physics. So for the physics physicians, this is something very easy name for them to remember. And we also have something called OpenJIJ. This is the open source library for Monte Carlo calculation. And you can use it with Python, very easy to use. So if you want to do optimization, if you want to do local simulation, you can use this and try it. And aging optimization calculation, this is one of the earliest open source resource available. The other thing is we have a product called JIJ Zept. This is the middleware for mathematical optimization by quantum and classical computing. So before I get into Zept as a product, I'd like to just talk us about why we are focusing on mathematical optimization. I'll talk about optimization as well as what are the examples of collaboration that we are having with our customer private businesses. So optimization computations can be used in a wide range of different scope. It can be utility, electricity, gas, or it can be used in transportation and logistics that is very close to your daily life. As well as telecommunication, more recently, we get a lot of interest about optimization computation or material development. And we are collaborating and developing different applications, working with the private businesses like Toho Gas. I can share some of the information that I can disclose to you. KDDI will be another company. We also have partnership with the overseas business with the infrastructure optimization. And this is also, again, public information. Toyota Tsusho also has a booth back there. And we do have this collaboration with the Toyota Tsusho. This is like a 3-organization collaboration also with Microsoft. This is the traffic lights. The timing of the traffic light can be controlled to ease the traffic jam. This can have a significant impact. Let me give you an example. If, hardware improvement for better mileage costs a lot of investment, and you have to wait until the new car's being sold. But if you change a small amount of the timing of the traffic lights, the traffic jam can be eased, as well as the fuelage, mileage can be improved. With the Microsoft, the research, about 20% of traffic jam, standalone waiting time can be reduced, according to their research. So this is an example of the optimization project that I was involved with. Now, but I'd like to spend more time about overview about our product called JIJ Zept, and what are the things that we can do around the optimization algorithm. So let me just start talking about what JIJ Zept can do. Now, mathematical optimization, especially the optimization for combinational optimization, in the context of quantum or quantum annealing, a lot of people are just focusing on making it very fast because calculation time is like very complicated. So spending shorter time or like a faster calculation is important. But mathematical optimization is old technology, even before AI becomes available. But it was a very rare that people are using this approach because when we talk about mathematical optimization, let's say we have this problem. We have to first quantify them, put the equation. You have to build an algorithm yourself. You have to describe the real world using the mathematical models. So this is like even a step before the faster optimization process. So representation with mathematical method sounds like a very complicated. And if we are trying to make a algorithm to solve this, so there are device unique decision model, right? Or Kulo would be another example where you have to have those parameters too. So real-world problem has to be represented in mathematical model, which is complicated itself, and convert that to intermediate representation itself is also complicated. You have to also fine-tune them for unique characteristics of hardware. And especially this layer, middle-aware layer tends to become the very huge bottleneck. Now, JIJ Zept, here's the JIJ Zept can play this can be automated as a process. So developers themselves, they don't have to do the finite detail tunings. The hardware that you want to use can be maximized its support by working with our automation process.
ではですね、じゃあ
And with that, I'd like to just tell you how we are doing that. This is actually core part of my presentation. Now, our approach is to have an interface and a data structure. Our approaches to the interface and data structure are very different from traditional approach. And these are the benefits that we are providing. First off, it's very easy to use modeling tool. And the modeling tool can be also be converted into mathematical model. So the compiler is very powerful. I can make it easy to convert it to mathematical model. We are also supporting multiple different hardware types. And so, let's say, optimization calculation is you need a lot of qubits right now, and it's not like chemistry. You have to look into the farther future where technology is much more evolved. So, while working on supporting multiple hardwares today, you can, when the qubit becomes available, you can switch that approach to the quantum computing when the technology becomes available. We also have, during a POC, you will do the best practice benchmarking. Now, it's very difficult. You have to be an expert to identify right KPIs. Right? You don't want to do randomly. You have to choose right benchmarks. But that benchmarking tool will make it very easy and simplify the process to identify what would be the KPIs or index that you want to do. So with Zept, tuning becomes easy. You can choose different hardwares. Therefore, the POC process can be much more simpler than otherwise with our tool. So I'd like to talk a little more details about how it is easy to use. So with the quantity annealing, you probably have written Kumo or Ising model if you're involved in the process. You don't need to know those the coding. You just put the objective function, and it's So Kubo is in model on the left-hand side. You don't have to know anything of them in order to do the modeling. With the Python interface, if you know how to use Python, it is very intuitive process. And the other thing is when you optimize the computation and you look at the answer, is coding wrong or the question raised being wrong? You don't know. So this our interface can show you actual function. And so you can implement it in the source code, and you can also check their function at the same time. Next, I'd like to talk about mathematical model compiler. And it's more than easy to use because we have a unique structure inside. Model and instance or data set are clearly being divided because our modeling model is using something with the constraint detection. And and software actually can make a much better interpretation of what it is. And because it can use algebraic model to show different constraints. Constraints can be detected automatically by our software. And based on that constraints, very efficient Kubo get compiled. And looking at the list of the constraints, and the engineers who are manually doing that is using this Kumo approach. And that, with our compiler, so that algebraic detection constraints can be detected so that it can tune the parameter with the fitting into Kubo compiler. Kubo compiler, once it gets into Kubo compiler, you have to calculate penalties with the parameter tuning, and the parameter tunings can be also be done with our automatically with a feature. So that's the summary of what I just said. It first detect constraints. It make a very efficient Kubo, and domain wall encoding is just one example of doing that. And user will automatically choose that if that's the best solution for that. You don't have to choose it as a user. And after the iteration process happens with a Kubo optimization solver format, it gets run iterations so that run the iterations so that parameters get automatically being tuned. So middleware compiler system like that, you don't, as a user, don't have to do any tuning to improve the performance of the hardware. And guess what? The hardwares, you can choose different multiple hardware sets. So the very advantage would be one example. Microsoft has a QIO on Azure Quantum Platform. Fujitsu also has a platform, have a hardware called Digital Annealer. And they are very unique characteristics, like Fujitsu's version 4, most recent one, have added a lot of features, but compiler will actually be able to adjust based on the version, the type of hardware. And what we are developing as a new feature is the automatic construction of quantum circuits. And in compiler, in our case, we are actually focusing on slightly different layer. This is something close to algorithm generator. In the optimum computation, deciding the Kubo is the standard approach. But in a more recent approach, subsurface quantum annealing is used as an approach. In using the relative relationship of the constraints and fill into the composing to the circuit. So users makes this mathematical model. It gets parsed through this to make a very efficient quantum circuits. And I can choose a hybrid strategy. What would be the parameter that should be used in terms of the optimization? and it will automatically create quantum circuit that's being optimized for you. And this is something that we are developing right now. And this hybrid quantum circuit, so KILAX, well, the fastest one, or IBM quantum computing, and this can be connected. And this output and quantum circuit that's being optimized can be used into work with via ticket. The point is there are a lot of different interfaces that can be used for that output. Now, our middleware can tune it automatically. And if you want to run POC project with Zept, then there are a lot of walls, right? Especially when you want to collaborate with the users. You have to have a standard approach in terms of the data sets. And but JJ benchmark can play a great role into that. This is part of Zept. There are a lot of parameters that the user otherwise have to write. And there are many of the problem list has to be done, compiled. But parameters will be listed, hardwares are listed. So with that, the hardware has already been tuned, and you will be able to do the benchmarking quite simply. So how the Zept is being used, and I'd like to share some of the screenshot examples from the and give you some ideas. So we have a cloud Zepter environment provided for our users. Zept all has all required tool set as soon as you come into our environment. Or you could have an API client installed in your machine, and you can go to cloud service where our middleware service is available. So you have a choice between these two options. So you'd like to use Zept to optimization computation. We have to create algorithmic, and you define variable, and one for constraints get written. And this is all you have to do. Everything will be done automatically. You don't have to pay attention to doing fine-tuning yourself. And next, you would put data. And so that algorithmic model and the data get combined, and then it will be presented with the analysis, highlighting where the constraints are broken, where the constraints are being protected, and everything will be solved. Zept will give you an answer to that. It's as simple as that. Zept is not only supporting quantum, it's also supporting classical. ACP algorithm is also being supported. We're running public data beta program. Infrastructure users are the main users right now for the beta version. And you can apply directly from this link if you're interested in using this. So please come access public beta. You can apply for that, and we'll be happy to welcome you. So with that is the I have introduced you with Zept, and also generator for quantum circuit. If you're interested in more details, I'll be in this event until the end. Please find me and talk to me, or you can go to that link, and please follow us on Twitter. Thank you very much for your attention.